So we're going to write out the balance equations, and then we'll do the solubility products for each of the following compounds. So we're going to do the equations over here, and then we'll do our KSP expressions over here. All right, so for this one, when copper bromide breaks down, all right, what are we going to get? We're going to end up, we'll just write our products over here. We're going to get copper plus and bromine minus. Right. For zinc oxide, we're going to get zinc plus 2 plus O minus 2. For silver chromate, we would get 2Ag plus CrO4 minus 2. For mercury chloride, we're going to get Hg plus 2 plus 2Cl minus. Gold chloride, we would get Au plus 3 plus 3 chlorine minuses. And then last but not least, manganese phosphate, we are going to get 2 MNs at plus 2, and that's a lie. We're going to get 3 MNs at plus 2, and then we're also going to get 2 phosphates each at minus 3. So if we're wondering, hey, what's our KSP expressions? So, right, KSP equals, and it's going to be copper plus bromine. Right. The next one, KSP equals zinc plus 2 and O minus 2. All right, for silver chromate, KSP equals, okay. Remember, we don't include the 2, the coefficient in here. So this is just Ag plus squared over COR4 minus 2 to the first. All right, so for mercury chloride, it's KSP equals Hg, right, plus 2. And then again, it's Cl minus, and then the 2 coefficient. Right, we should never, ever, ever, right, have a number or a coefficient in any of these brackets. All right, KSP equals, right, the molar concentration of gold, right, times the molar concentration of chlorine cubed, and then last but not least, manganese phosphate, all right, which is going to be Mn plus 3 squared, or no, I keep doing this wrong, Mn plus 2 cubed, sorry about that, and then times PO4 minus 3 quantity squared. All right, and number 2, we're going to find out the molar solubility of saturated silver 1 sulfide solution, Ag2SO3, and we're given the KSP value. So we first need to write out what is happening here with the dissolution of silver sulfate. So we got to start with writing out that. So it's Ag2SO3, and it's going to produce 2Ag plus an SO3 minus 2. All right, so we know KSP, okay, equals Ag plus, right, squared times SO3 minus 2, excuse me, and then this is going to be to the first power. Now we need to do an ice chart here. When this breaks apart, right, let's put that like this. Ice. We don't care about the solid because it's not involved in equilibrium. So initially, these are always at 0 to start these problems off. This is going to appear at 2x. This just appears at x. Actually, let's call this S for this chapter for solubility, but it's the same thing. All right, so at equilibrium, this is 2s and this is s. And we're going to plug these values in to here and here. So KSP, which is 1.5 times 10 to the negative 14th, okay, equals 2s quantity squared times s, right? Or 1.5 times 10 to the negative 14th equals 4s cubed. All right, square the 2 squared, s squared times s is s cubed. All right, let's solve for s. So we take that 1.5 times 10 to the negative 14th. We're going to divide it by 4. And then we're going to take the cube root and raise it to the 1/3 power. All right, raise it to the 0.3333333, or if you have the cube root button, that's fine too. And it's always easy to express these in scientific notation. So the molar solubility is 1.55 times 10 to the negative 5th molar. 3, silver chloride has a larger KSP than silver carbonate. KSP of silver chloride is 1.6 times 10 to the negative 10th, right? And KSP has silver carbonate has a KSP of 8.1 times 10 to the negative 12th. So which cell is more soluble, and justify your answer? Okay, so let's just, all right, so AgCl and Ag2CO3, all right? 1.6 times 10 to the negative 10th and 8.1 times 10 to the negative 12th. So what we want to do here is, without doing a ton of math, we can kind of do some shorthand math and some, oh my gosh, I'm blanking on the word, estimating to help us out. So the formula, right, because there's just two compounds, or sort of two elements put this together in a 1-to-1 ratio, KSP is going to be equal to S squared. Right here we have 3 total species. We have 2 silvers and a carbonate. So when we have a formula of M2X or MX2, the solubility is always going to be equal to 4S cubed. Okay. So what we're going to do next is we're just going to figure out what's the exponent going to be, like a rough estimation. What is the exponent going to be, right? So for this one, right, we have negative 10. Well, if we take the square root of negative 10, that's just doing negative 10 divided by 2, right? Our exponent is negative 5. Let's do the same thing here. This is negative 12. We're going to take the cube root of negative 12. So when we take the cube root of negative 12, all right, we get negative 4. All right, we're getting negative 4. So just by looking at the difference here, we can make the argument that silver carbonate, despite having a smaller KSP, will actually have a larger molar solubility, right? And we can explain why the molar solubility is going to be bigger, right, just by estimating of silver carbonate versus silver chloride. All right, 3, calculate the concentration of ions of the following saturated solution. So I minus in silver iodide with the Ag plus as 9.1 times 10 to the 9th. All right, so for this one, okay, sorry, I just misread that. All right, so for this we have AgI. Well, in silver iodide goes through its dissolution, it becomes Ag plus and I minus, right? It's a 1-to-1 ratio. So whatever the concentration of one of them is, it's the concentration of the other one. So the answer is 9.1 times 10 to the negative 9. For B, so aluminum hydroxide, so we want to find out what's the concentration of the aluminum if the concentration of OH is 2.9 times 10 to the negative 9. Right, so for aluminum hydroxide, when aluminum hydroxide is placed into water, it's going to become an aluminum of +3 and 3 hydroxides. That means when this is done doing its dissolution at equilibrium, this is S and this is 3S. So if we know that the concentration of the hydroxide is 2.9 times 10 to the negative 9, that's 3 times higher than the concentration of aluminum because of this 3 in front. So we're just going to take that number, we're just going to divide it by 3. So 2.9 times 10 to the negative 9, right, and we're going to divide that by 3. We're going to get 9.66 or 9.67 times 10 to the negative 10th is the concentration of the aluminum ions. Excuse me. All right, so for 5, for A and B, we're given the solubility in grams per liter, and the goal is to find out what's KSP. So in order to solve any KSP problem, the very first thing we need to do is we need to get KSP into its proper units. And to solve for any KSP problem, we have to be in molarity, moles per liter, right? So we got 7.3 times 10 to the negative second grams per liter. We got to convert this to moles per liter. Well, that's easy because there is 125.88 grams in a mole. So that's going to give us our molar solubility. Right, so let's write that out. So 7.3 negative 10th, or sorry, negative second, divided by 125.88. So our molar solubility is 5.799, and we can provide 5.8 times 10 to the negative fourth. All those nines are going to round up to 8 there. All right, so 5.7 to the negative fourth molar. That is the molar solubility. Okay. Strontium fluoride, when it breaks down, it's going to produce Sr plus 2F minus. So if we do our ice chart, 0, 0, plus S, plus 2S, S plus 2S. So KSP, okay, equals S times 2S squared, or equals 4S cubed. Well, we know S is the molar solubility, so KSP equals 4 times 5.8 times 10 to the negative fourth quantity cubed. So 5.8 negative fourth to the third power, and we're going to multiply that by 4. And we get 7.8 times 10 to the negative 10th. That is the answer for KSP. Okay. For B, same idea. So we have 1.08 times 10 to the negative 8th. All right, and we're going to divide that by the molar mass, which is 106.87 to get the molar solubility. Very unsoluble item here. 1.08 times 10 to the negative, negative 8th divided by 106.87. So our molar solubility is 1.01 times 10 to the negative 10th. All right, iron hydroxide, when placed into water, is going to produce Fe plus 3 hydroxides, each has a minus 1. If we ice this up, we're going to get 0 SS, 0 3S, and 3S. So that means KSP equals S times 3S cubed, or 27 S to the fourth. All right, again, S is 1.01 times 10 to the 10th, so KSP equals 27 times 1.01 times 10 to the negative 10th cubed. So we're going to get a ridiculously small number right now, times 27. Oh yeah. So this KSP is 2.79 times 10 to the negative 29 equals KSP. That's for B. All right, 6. The molar solubility of magnesium carbonate is 4.2 times 10 to the negative 6. What is the KSP for this compound? All right, so for this one, if we just take a look, magnesium carbonate, when this breaks down, is going to turn into manganese and carbonate. Right? So because this is a 1-to-1 ratio at equilibrium, it's just S and S. So KSP equals S squared. So KSP is going to equal our molar solubility, 4.2 times 10 to the negative 6. And we're just going to take that value and we're just going to square it. So 4.2 negative 6 quantity squared. 1.76 times 10 to the negative 11. All right, and then last one, 7. All right, 7 is just like 5. We have an experiment. We're basically given the grams per liter solubility. We're not basically, that's what we're given. Right? So the first thing we're going to do is we're going to take this 0.0059 grams, and we've got to convert it into moles per liter. So divide that by 147.63. That gets you a mole. So that means our solubility, our S, is 0.008. 3.99 times 10 to the negative 5th. Actually, this perfectly rounds up to 4. So 4 times 10 to the negative 5th. And so that is our solubility. So strontium carbonate, when it breaks down, it dissolves, it gets strontium and carbonate. And just like the one above, it's a nice 1-to-1 ratio. So at equilibrium, it's going to be S and S. So that means KSP equals S squared. KSP equals 4 times 10 to the negative 5th squared. So if we're going to use these numbers, if you square that, that's going to be 1.6 times 10 to the negative